Okay, so what we want to look at now is you want to look at obtaining the inverse of a matrix, square matrix, by using row operations, right? And to get this inverse by using row operations, we will need something called elementary matrices, right? So first, first parts of this lecture, what we're gonna talk about would be the elementary matrices, and then eventually we'll get on to move on to getting the inverse of the matrix, a square matrix, right? Okay, so this method of getting the inverse of a matrix is different from what you probably would have seen in 1180, where what you did is to get your inverse, you form your adjoint matrix and then you multiply the adjoint matrix by 1 over the determinant of A, right? Okay, so this would be this method that we're going to look at now. It's a different method, right? This method here, while it would work for say like smaller matrices, getting this adjoint, right, which requires you need to get determinants of submatrices, and over here also you'd want to get determinant of the entire matrix, right? This calculation is it's not efficient when the n starts to get large, right? So this method over here that we're going to look at, right, where we're going to use row reduction, right, it would be more efficient than this formula here using the adjoint, right? Okay. Right, so you'd need a couple things. Well, let me just remind you of what an identity matrix is, right? Okay, so this is an example of a 2 by 2 identity. Notice the notation that I use is I2 over here, right? So 2 by 2 identity is square matrix size 2, right? Where you have ones on the diagonals and 0 everywhere else, right? 3 by 3 identity, which is we denote by I3, right, is, well, 3 by 3 matrix, ones on your diagonal and 0 everywhere else, right? And you can keep going with that definition, right? So this is an I4 over here. I4 is your 4 by 4 matrix, right? So this is a 4 by 4 matrix where you have ones in the diagonal and 0 everywhere else, right? Okay, so why they call it identity matrix is because it's a multiplicative identity, right? Which means that if I have a matrix A and I multiply it by the identity, right? I notice this here, this matrix A that I'm multiplying the identity by, right? This doesn't have to be a square matrix, right? Okay, so for example, this matrix A over here, and I'm going to be multiplying by an identity, right? This matrix here is 2 by 3, right? Okay, so the A is the A over here, this matrix A is 2 by 3, and I'm multiplying it by an identity, and I'm going to get back to same matrix A, right? So that's an example of what I'm saying here, right? I have a matrix A, I'm multiplying on the right hand side by an identity matrix, and I'm going to get back to same matrix, right? So A times this identity over here gives me back to same matrix, right? So that's what I mean by multiplicative identity, right? A times this multiplicative identity means that if I multiply A by this multiplicative identity, well, nothing happens, and I get back the same matrix A, right? In order for this matrix multiplication here to be well defined, right, the number of columns here needs to match the number of rows of the identity, right? So you see over here, here I have a 2 by 3 matrix A to start off with, and I'm going to multiply by identity, right? But for this matrix multiplication to be well defined, the number of columns of A has to be equal to the number of rows of the identity, right? So if I'm multiplying A by an identity matrix, and the identity matrix is on the right hand side here, right? The size of this identity matrix, remember this is a square matrix, or if you want the number of rows of the identity matrix has to be equal to the number of columns, right? And A is a 2 by 3 matrix, so A has 3 columns, which means that this would need to be a 3 by 3 matrix, right? And when you do your matrix multiplication over here, and you should check, right, that if you multiply this matrix A by this 3 by 3 identity matrix, you're going to get back the same matrix over here, A, right? Right, and also if I have the matrix A, right, and this matrix A again is not necessarily square, right, this would also work if A is square, right, just that the A not being square is a more general case, right. Okay, so if I have A over here, right, and I'm going to be multiplying on the left hand side, right, then the number of columns in this identity matrix over here has to match the number of rows of A, right. Okay, and the number of rows of this matrix A is 2, right? So your matrix multiplication over here, this is, you're gonna, for this to be well defined, if this is 2 by 3, then this matrix over here has to be of size 2 by 2, right? Okay, and you can check when I have this 2 by 2 identity, and I multiply on the left hand side by this matrix A, right? When you multiply it out, you're gonna get back the same matrix A over here. Alright, so I'll need some definitions, right, and some notation, right? Okay, so I have a matrix A, right, and what I'm going to do is I'm going to do a row operation on it, right? So this is my matrix A over here, and this is a row operation, so the same type of row operations that we saw before, right? We have three types, where I can switch two rows, I can multiply a row by a non-zero scalar, or add a multiple of one row to the next row, right? Okay, so in this example over here, what I'm doing is I'm switching two rows over here, right? And I'm calling this row operation, I'm calling it epsilon here, right? Okay, so I have a matrix A, and here I do the row operation where I switch two rows, right? And when I switch two rows, what I'm doing is I'm switching row 2 and row 3, and notice, okay, so this is my original matrix over here. And what I do is I switch to two rows, right? So this result over here, this resulted matrix is what I get when I switch row 2 and row 3. So the row 2 comes to row 3 position, and the row 3 goes to row 2 position, right? Okay, so this, if I have, and this is my original matrix A over here, and I'm calling the row operation, which is the same row operation where I switch row 2 and row 3. I'm calling that epsilon. Then this epsilon A over here, this is just a certain piece of notation, right? It means to this matrix A over here, I'm going to apply this row operation epsilon, right? So this is my original matrix A, and what this means is I'm going to take A and I'm going to apply a certain row operation epsilon. So the A is going to be modified down to epsilon A, right? And the row operation, it is row 2 exchange with row 3, right? So if this is my original matrix A over here, where this is the row 2 and this is the row 3, then to get epsilon A, what I'm going to do is I'm going to apply the row operation row 2 exchange with row 3, which means I'll have the 5 6 will come up to the second row, and then the 3 4 will go to the third row, right? Okay, so notice it's just the same thing as what I did when I was doing normal row operations over here, right? It's just that I'm keeping track of the row operation, right? And I'm calling this, say this first row operation over here, which is epsilon. I'm calling it epsilon there. So epsilon A over here just means I'm going to take A and apply this row operation, row 2, exchange with row 3, right? Okay, so really it's the same thing as what we had before when we do row operations. It's just that the epsilon A means that you have A and you apply a certain row operation to it, right? Okay, so our next definition here is an elementary matrix, right? So what do we mean by an elementary matrix, right? An elementary matrix means that I have an identity matrix to start off with, and I just apply a certain row operation to it, right? One row operation I apply to the identity matrix, right? Okay, so for example, over here I have this 3 by 3 identity matrix here, right? And the row operation in this case is I'm going to add 2 times row 1 to row 3, right? So remember this notation over here. The target row is the last row here, right? So I'm going to change the row 3 here, right? So 2 times row 1 plus row 3, right? Okay, so if this is my identity matrix over here, right? What I'm going to do is I'm going to apply a single row operation to it, right? And the single row operation is this one here. And applying that single row operation means that I'm going to multiply, in this case, multiply first row by 2 and add it to the third row, right? In which case I'm going to get a 2 0 1 over here on the bottom, right? Okay, so this is my original matrix I3, and this is when I apply a single row operation to I3, right? And notice I'm using the same notation as what I did above here, right? So this is the original matrix I3 over here. And I apply a single row operation epsilon over here. So this notation epsilon I3 means that it's I3 after you apply that single row operation, right? Okay, so you have an identity matrix, you apply a single row operation, and that's an example of an elementary matrix, right? So if you have an identity matrix and you apply a single row operation to it, then that is always an example of what's called an elementary matrix. Okay, so if you want some further examples of elementary matrices, all four of these here are elementary matrices, right? Okay, so for example, this here, what you did is you started off with a 2 by 2 identity, and what you did is you applied a single row operation where you multiply row 2 by minus 3, right? Okay, so you multiply the second row of I2 by minus 3, right? So you apply a single row operation to an identity matrix, and you get this elementary matrix here, right? Okay, this is also an elementary matrix. What you had was I4 to start off with a 4 by 4 identity, right? And what you did is you exchange row 2 and row 4, right? Okay, and when you exchange row 2 and row 4, that's what you get over here. So this is also an elementary matrix, right? This here is an elementary matrix where you multiplied row 3 by 3 and you added it to the first row, right? So you started off with 3 by 3 identity and you apply a single row operation here, right? Okay, and this here is sort of trivial elementary matrix. You take the first row of I3 and you multiply it by 1. Okay, so this is a sort of special case over here if you want, right? Or elementary matrices was more look like probably these first three over here where you actually do something, right? Alright, so we'll need some more notation here, right? So let's consider I have this matrix A over here, which is this 3 by 2 matrix, right? I'm going to apply two row operations to it, right? And first row operation is I'm going to switch two rows, and then the second row operation I'm going to multiply a row by a non-zero scalar, right? Okay, so the first row operation I'm going to call epsilon 1, and the second row operation I'm going to call epsilon 2, right? Okay, so our normal way of applying row operations is here I have a matrix A and a normal notation. Okay, so first one is you're going to switch row 2 and row 3, right, which is what we do over here. And then the second one over here, what we're going to do is you're going to multiply row 1 by 2, right? So normal notation that we have, that we saw before, right? Okay, and now what we want to do is we want to see what's the new notation that I'm going to use, right? So remember, A is this matrix 1, 2, 3, 4, 5, 6, right? Epsilon 1 is switching row 2 and row 3, and epsilon 2 is multiplying row 1 by 2, right? Okay, so this process over here of going, starting with matrix A, applying your first row operation, and then applying the second row operation, I can write using my new notation, right? Okay, so I have matrix A over here, right? And what this epsilon 1A means is I'm applying epsilon 1 which is switching row 2 and row 3. Right, so apply epsilon 1, which is switching row 2 and row 3, right? And notice that's what I do, right? So this is A over here, and epsilon 1A means that I switched row 2 and row 3, right? And then epsilon 2 was multiplying row 1 by a non-zero scalar 2, right? Okay, so to this epsilon 1 over here, epsilon 1A, which is A, right? Then I applied epsilon 1 to it. I'm going to now apply epsilon 2 to this one over here, right? Which means I'm going to take this row 1 over here and multiply by 2, right? Okay, I notice I get the same result as what I did when I was just using my normal notation as before, right? So this is the A over here, and then this is the epsilon 1 over here, and then this is the epsilon 2 epsilon 1A, right? So this is the A, I apply epsilon 1, and then I apply epsilon 2 on top of that, right? So that's what this is here, right? this is A over here, apply epsilon 1, which is switching row 2 and row 3, and then apply epsilon 2, which is multiplying row 1 by 2, right? Okay, right, so this is how you want to read this. Is I had A over here, right, to start off with. This is my original matrix, and I applied two row operations to it, epsilon 1 and then epsilon 2, right? So I had A, applied my first row operation, which is epsilon 1, and then applied my second row operation, which is epsilon 2, to get me my result, right? Which is A apply. So this is A over here. You apply epsilon 1 and then you apply epsilon 2, and this is the resultant matrix, right? Epsilon, if I have a matrix A, what this notation over here means, that it means that to your matrix A, I apply a row operation epsilon 1, then I apply a row operation epsilon 2, right? So this is when I had two row operations and I apply it in that sequence, right? I do epsilon 1 first and then I do epsilon 2, right? Now I could have three row operations, I can have four row operations, I can have any finite number of row operations, right? So that is what the statement is over here now, right? This notation over here, epsilon 1, epsilon 2, up to epsilon p, whereas this small p is the number of row operations, means that I start with A and then I apply row operation epsilon 1 first, then I apply row operation epsilon 2, and I keep applying row operations and until I apply my last row operation, which is epsilon p, right? So this is what I say in the notes, right? This matrix over here is the matrix that you get when you apply row operations epsilon 1, epsilon 2 up to epsilon p on your original matrix A in sequential order, right? And what I have over here is I have a case when the small p is equal to 2, right? I have A and then I apply epsilon 1, then apply epsilon 2, right, in sequential order. Okay. Alright, okay, so this over here is in order to show, to justify getting the inverse of a matrix via row operations, right? This really is the sort of key result that we want to consider, right? So this one is important for us, right? Okay, so, well, what is this left-hand side over here, right? This left-hand side is what we just saw, right? I have a matrix A, some matrix A, and I'm going to apply a row operation to it, right? So I have matrix A and then I apply a row operation to it to get a new matrix, right? Okay, so an example of that is I have this matrix A, which is this 3 by 2 matrix, and the row operation is switching row 2 and row 3. Okay, so epsilon A is what I get when I apply a single row operation called epsilon to A, right? So I exchange the bottom two rows, right? I exchange row 2 and row 3, right? Okay, so that is what this left hand side is, right? And we saw that already, right? Okay, the right hand side over here, what this is saying is that so this over here, this left hand side is I have A and I apply a single row operation to it, right? What this right hand side is saying for me now is that this over here, this is A, and then this is epsilon of an identity matrix, right? So this is an elementary matrix over here, right? Okay, and it's the same epsilon over here as over here, right? So on this right hand side, what I actually have is I have matrix multiplication, right? This over here, this is A over here, and epsilon IM just by itself, right? This over here, this is an elementary matrix, right? Okay, so what this is saying here is that if I have my matrix A over here and I multiply by the elementary matrix corresponding to the epsilon that I'm looking at, right? Then multiplying by this elementary matrix has the effect of performing the row operation on A itself, right? Okay, so on the left hand side over here I have the matrix A, and this notation means do the row operation epsilon on it, right? This over here on this right hand side, this is, if we forget about the A for the time being and you just focus on the elementary matrix epsilon IM, right? What this part means is I start off with identity matrix, right? Notice the identity matrix is of size m, where m is the number of rows of A, right? Okay, so I have this IM, and the same epsilon as I had across here, I applied it to this identity matrix to get an elementary matrix, right? And what this elementary matrix is doing for me, it's carrying the information about the row operation, right? When I do the matrix multiplication of this elementary matrix times this matrix A, right, it has the effect of simply doing the row operation on A, right? So it's probably easier if you see an example of this, right? Okay, so this is my matrix A over here, right, that I'm going to use in my example. And the row operation is switching row 2 and row 3, right? So epsilon A means to the matrix A, I'm going to switch row 2 and row 3, right? Okay, so now what I'm doing is I'm going to look at my right hand side now over here, right? Okay, so here what I have is I have uh, a 3 by 2 matrix, right? So small m is equal to 3 over here. So I'm going to consider uh, 3 by 3 identity over here. So the im over here, the small m is equal to 3, right? Okay, that's because I want this matrix multiplication to be well defined, right? Okay, so I need three columns in this identity matrix in order for this matrix multiplication in this case to be well defined, right? Okay, so I have I3 over here, and notice what I'm going to, the same row operation, which is exchange row 2 and row 3. I'm going to apply that to this I3 over here, right? So when I exchange row 2 and row 3, I get 1 over here, so I get 0, 0, 1, and then 0, 1, 0, right? So you want to notice this is no longer the identity, right? Okay, and what I'm saying over here is that this elementary matrix now carries the information about switching row 2 and row 3, right? Because if I take this over here and I multiply it against A, right? So if I take this elementary matrix, right? And I'm saying that this one over here contains the information about switching row 2 and row 3. If I take this and multiply it against A, what it will do is it will actually switch these two rows for me, right? And you can check it, right? You can do the multiplication, right? If I take 1, 0, 0, right, and I multiply it against this matrix over here, what I will do is when I take 1, 0, 0 and multiply it against the entire matrix, what I'll do is I'll pick up the first row, right? 1, 2, right? And when I take 0, 0, 1 and I multiply it against the entire matrix, right? What I will do is I will pick up now the last row, right? So the 0, 0, 1 by the entire matrix over here would give me the 5, 6, right? And then finally, when I use the third row over here and multiply it by this entire second matrix, what I will get is the fact that I have a 1 in this second position. I pick up the row 3, 4, which is this 3, 4 over here, right? Or if you're not happy with that explanation, you could just simply multiply it out, right? And when you multiply it out, what you notice is that when you do a multiplication by this matrix, the row 2 and the row 3 will switch, right? Okay, so when you take this elementary matrix and multiply by my original matrix A over here, what it does is it switches row 2 and row 3, right? Okay, so this elementary matrix over here is carrying the information to exchange row 2 and row 3, right? In other words, if I want to switch row 2 and row 3 for this matrix over here, right, I can multiply by a certain matrix, right? A certain matrix here. And that certain matrix is an elementary matrix, right? Okay, so if I want to switch row 2 and row 3 one more time, if I want to switch row 2 and row 3, right, what I do is I multiply by a certain elementary matrix, right? Now, how do I get that elementary matrix is I use my identity, right, that I have. And what do I want to do, right? What I want to do is I want to switch row 2 and row 3, right? So what I do is I switch row 2 and row 3 on the identity, right? And that gives me this one over here, and now this is carrying the information, right, to switch row 2 and row 3, right? This first one here is carrying the information to switch row 2 and row 3. And when I multiply this matrix over here against my original matrix, it will do the switch of the row 2 and row 3, right? Okay, so your elementary matrix over here, right, what it does is carries information about the row operation for you, right? And in this case, it carries the information about this row operation, which is switching row 2 and row 3. Alright, so what did we just see, right? What we saw is if I have a matrix A over here and I want to do a certain row operation on it, right? What I could do is I can do the row operation first on identity matrix, right? Right, I can do the row operation first on an identity matrix, right? And then what I can do is I can do the row operation on the identity matrix, right? And that would give me an elementary matrix, and multiplication of that elementary matrix by A has the effect of doing my row operation for me, right? Okay, so that's when I have a single row operation, right? And if I have now if I have more than one row operation, right, I can actually do the same thing, right? So here I have a matrix A, right, and I'm gonna apply a sequence of row operations, right? I'll give you an example over here. So I have a matrix A, and I'm gonna apply a sequence, which is sequence consists of two row operations over here, right? So this is my matrix A, right? First one is switching bottom two rows, and then the second one is multiplying row one by two, right? So here to go from here to here, I switch uh, two bottom rows, and here to go from here to here, multiply row one by two, right? Okay, so this is A, and epsilon 1A means I switched row 2 and row 3. And epsilon 2, epsilon 1A means that to this result, I apply epsilon 2, which is multiplying row 1 by 2, right? Okay, so this is A, and then I apply two row operations to A, right? And what I'm saying now is that I can, if I have a and I can apply, if I have a and I apply two row operations to it, right, to get a new matrix, right, which is this one over here, I can achieve the same result by multiplying by suitable elementary matrices, right? So this is my matrix A, this is the original matrix, and this elementary matrix over here is telling me to switch the bottom two rows, and this elementary matrix over here is telling me to multiply row 1 by 2, right? Okay, so this is my original matrix. When I multiply first by this elementary matrix in the middle, right, what that does is, if I just consider the product of these two, right, then what that does is switches row 2 and row 3, right? And now once I've worked out that first product over here, once I multiply by this one, it has the effect of multiplying this result, multiplying the first row of this result by 2, so I will get a 2, 4 over here, right? Okay, so one more time. Doing this product over here of your two rightmost matrices, this would give me epsilon 1 A, right? So that would give me this one over here, right? Multiplying this matrix here by 1, 2, 3, 4, 5, 6 gives me this 1, 2, 5, 6, 3, 4, right? So multiplying this middle matrix by the last matrix has the effect of switching your two rows over here, right? And then multiplying by this first one out in front over here has the effect of now taking the result from here and then multiplying your first row by 2, right? So you're going to get a 2, 4 over here, right? Anyway, so here what this is how you want to read this is I have matrix A over here, and I'm going to apply row operation epsilon 1 and epsilon 2, right? And to apply row operation epsilon 1 and epsilon 2, I can do it by multiplying by suitable elementary matrices, right? Okay, so to apply epsilon 1 and epsilon 2 to A in that order, I take A, multiply it by an elementary matrix containing the information for epsilon 1, which is this one over here, and then multiply it by elementary matrix containing the information about epsilon 2, which is this one over here, right? So this matrix over here contains the information for switching the bottom two rows, and this one over here contains the information for multiplying the first row by 2, right? Okay, and when you do this entire matrix multiplication, so this is the original matrix A, multiply by this one, okay, this will switch the bottom two rows for me, and then multiplying by this one would multiply multiplying by this matrix over here would multiply the first row by 2, and that would give me the end result, right? Which is what I would have when I apply two row operations, epsilon 1 and epsilon 2 to A, right? Which is this here. Right, okay, so I inserted an extra line of working over here. Hopefully this should be easier to see, right? So, right, so I have matrix A over here, right? And I'm going to be applying two row operations instead, epsilon 1 and epsilon 2 in that order, right? Epsilon 1 is when you switch the bottom two rows, and epsilon 2 is when you multiply your first row by 2, right? Okay, and what I'm saying here is that so for this matrix A, what I did is I apply epsilon 1 and epsilon 2, right? And what I'm saying is I can achieve that by multiplying by corresponding elementary matrices, right? So this elementary matrix over here, this one contains the information for switching the bottom two rows, and this one over here contains the information for multiplying row 1 by 2, right? And let's see if that works for me, right? So this is what I have, right? I'm looking at this right hand side, and when I do this multiplication over here, okay, of the multiply the last two, the rightmost matrices, okay, the ones on the right, on this right hand side, right? When I multiply this matrix against this one, what the effect of it does, it switches the row 2 and row 3, right? And you see that that's over here, right? Okay, and then multiplying by this one over here, right? This first one, well, now what this will do is this will multiply row 1 by 2, right? So you get a 2 over here and you get a 4 over here, which is this 2 over here and this 4 over here, right? Okay, so okay, one more time. If I have this product over here multiplying by this first matrix here, switches the bottom two rows, and then multiplying by this matrix over here out in front, right? What this will do is this will multiply row 1, sorry, by 2, right? So I'd get a 2 here and a 4 here, right? So what this one does for me is it switches row 2 and row 3, and what this one does for me is it multiplies row 1 by 2. Right, so let's take a look at this example. I have this matrix A over here, and I'm going to apply this row operation first, right, which is multiplying row 3 by 2, right? Okay, so this is the original matrix A, right? And I multiply row 3 by scalar 2, right? So I get a 10 over here and I get a 12 over here, right? Right, and now what I'm going to do is I'm going to reverse this, right? So how can I reverse this, right? What I want to do is I want to get back to what I had over here, right? Well, how I can get back to what I had, right, is, well, okay, going from here to here, I multiply row 3 by 2, right? Okay, so to get back, if when I do a next row operation to get back what my original matrix, I want to reverse this multiplication by 2, and then all I could do is just multiply by half, right? So to this matrix over here, right, this with the 10, 12 in it, I'm going to perform a new row operation, which is row 3 times a half, right? So this is row 3 now. I multiply row 3 by a half, and then I get the 5, 6, right? So I get back my original matrix, right? Okay, so this here, I started off with this matrix here. I did this certain row operation, which was multiply row 3 by 2, right? So I got this 10, 12. And what I did is I reversed what I did, right? So to reverse the effect of multiplying row 3 by 2, right? What I do is I multiply row 3 now by a half, right? So multiplying by a half would give me 5 here and a 6 here, right? Which would reverse the effect of multiplying by 2, right? Okay, so this was my original matrix A. I did a row operation, which is 2 row 3. And in order to reverse or to invert the operation that I did, right? What I do is, because I multiplied by 2 over here, multiply row 3 by 2. To reverse the process, I multiply row 3 by a half, right? Okay, so this half row 3 over here is an example of an inverse of the row operation 2 row 3, right? Why it's called an inverse is because with this row operation, once I do this row operation, if I apply this one right afterwards, right, what it has the effect of doing, it has the effect of canceling out that row operation. So I just gonna get back my original matrix, right? So you see it's written here on the right hand side, right? So this is my original matrix A over here, right? I apply the row operation, which is epsilon, which is multiply row 3 by 2, right? And then to this over here, I apply the inverse row operation, right? And I'm denoting the inverse row operation of epsilon by epsilon to the minus 1, right? Okay, and the point is this epsilon to the minus 1 will cancel with this epsilon, right? Okay, so the epsilon to the minus 1, when I apply it now, it would reverse the effect of this epsilon, right? So it's as if it cancels, right? And you just get back your original matrix A, right? Or let me explain this a little more rigorously. I have matrix A over here. I apply a single row operation epsilon, and then when I apply the inverse of that row operation epsilon, the inverse of that row operation epsilon, right, has the effect of canceling the epsilon operation, right? So what I end up with is just my original matrix A, right? And you see an example here, right? Okay, so this is in the case of when epsilon was multiplying a certain row by a non-zero scalar, right? To reverse the effect of multiplying that row by a non-zero scalar, what you do is you just multiply the same row by the reciprocal of that non-zero scalar, right? So if this is 2 over here, you need to multiply by a half, right? So that's the inverse, right? And that works for anything. It doesn't have to be 2. If the row operation was 5 row 3, right, then the inverse would be 1 on 5 row 3. And that is what this is saying over here, right? This second part over here, right? If I have a row operation which is multiplying a row by a non-zero scalar, then the inverse row operation, right, and the inverse row operation is multiplying that row by the reciprocal of this scalar c here, right? And you see an example. 2 over here, the reciprocal of 2 is a half. Okay, and remember what I'm saying in this example, right? The idea is that this one over here, the epsilon inverse, will cancel the effect of the epsilon, right? Okay, so if the row operation was exchanging row I and row j, then what the inverse would be is, well, if you switch row I and row j to get back to your original matrix, you just switch it back again, right? So the inverse row operation is just the same thing, right? Because this would just mean that you just switch them back, right? And if your row operation is add a multiple of row I to row j, right, then the inverse row operation would be you just take back out that row from row j, right? In other words, if you added row I times c, right, then what you need to do for the inverse is you subtract row I times c from row j. Right, so let's see a couple examples of the inverse row operations, right? This notation here is a little different from what I have, but it's the same idea, right? Okay, so this is a matrix over here. What I did is this one over here going from here to here. I'm multiplying using the row operation 7 times row 2, right? So going from here to here, it's 7 times row 2, right? Okay, and then to reverse the effect of this row operation, if I want to get back to my original matrix, right, what I need to do is multiply row 2 by 1 on 7, right? Okay, and if I multiply by row 2 and 1 on 7, I get back my original matrix. And that's an example of 2 over here, right? Where in this case, the c is, for this example, the c is equal to 7, right? And it's R2 over here. You're looking at row 2, right? Okay, this example here, what you're doing, going from here to here, you exchange 2 rows, right? So that's the row operation. And if you wanted to reverse the effect of that, right, what you need to do is just exchange row 1 and row 2 again, right? So you'd get back your original matrix. So that's an example of this part 1 over here, right? If the row operation is exchanging row 1 and row 2, then the inverse row operation is just exchanging row 1 and row 2, right? So you get back to original matrix. Okay, and going from here to here, right, what you're doing is it's 5 times row 2 added to row 1, right? So 5 times the second row plus the first row, right? So this is 5 row 2 plus row 1. And if you want to get back to your original matrix, what you do is it's going to be minus 5 times row 2 plus row 1, right? So if I have minus 5 times row 2 and I add it to the row 1, I'd get a minus 5 over here, plus this 5 would give me 0, and I'd get back the original matrix, right? And that's an example of part 3 over here, right? If the row operation, and this one here is 5 row 2 plus row 1, then the inverse row operation is minus 5 row 2 plus row 1. Okay, so let's look at the definition of the inverse of a square matrix, right? So if I have A is a n by n matrix, right? And if I can find n by n matrix B such that A times B, right? So if I multiply A by B and B is on the right hand side, or I consider BA, right? In other words, B is on the left hand side, right? And if AB is equal to BA is equal to the identity matrix, then B is called the inverse of A, right? And we can write B as A inverse, right? So the B over here would be the inverse, right? If B satisfies AB is equal to BA is equal to identity, right? Right, you can show that in order for B to be an inverse, that it would only need to satisfy one of these, right? So in other words, you just need that the AB is equal to identity or the BA is equal to the identity, right? This is the starting definition to show that you can in fact drop off one of these conditions and all you need is just one of them, right? So either AB or BA, right? That takes more work, right? And the proof of that is across here, right? And they say that, right? So if a square matrix has a right inverse, then it has a left inverse, right? So in other words, if it has a right inverse over here, then it would have a left inverse, right? And the inverses are in fact unique, right? So if you have a left inverse and you have a right inverse, then the left inverse and the right inverse. So this is your right inverse and this is the left inverse. If the right inverse is equal, if it has a right inverse and it has a left inverse, then what this is saying is that they need to be equal, right? But this takes a certain amount of work, right? The point I want to make over here is that with this definition, one of these is sufficient to show that a matrix B is that this is an inverse, right? All you need to do is, if I have A and I found some matrix B such that A times B is the identity, then that would make B the inverse of A, right? Right, so let's see an example of this, right? Okay, so I have this matrix A over here and I have B, right? And when I do the multiplication, A times B, right? So A is just 2 minus 5 minus 1, 3, and B is 3, 5, 1, 2, right? And if I consider A times B, right, then A times B works out to be the identity. And if I also work out B times A, I will get the identity, right? So what that tells me is that B is actually equal to A inverse, right? So this is an example of B being the inverse of A, right? And because this definition is symmetrical, right, this actually means that, and looking at this example as well, right, if I start off with the B, right, and I consider the B and I multiply A on this side and I multiply A on this side, and in both cases I get the identity. That means if I start off with B, then A is the inverse of B, right? So A is equal to the inverse of B in this definition, right? So both of these, this definition over here, AB is equal to BA is equal to identity. It means that B is equal to A inverse, and it also means that A is equal to B inverse. Okay. Right, and then finally, a square matrix is invertible if it actually has an inverse, right? Okay, so let's consider this example here, right? I have an identity matrix, a 3 by 3 identity matrix, and then I have this row operation, which is um, taking 2 times row 3 and adding it to row 1, right? So that's this row operation epsilon over here, right? Okay, so 2 times row 3 plus row 1, right? So if I apply this epsilon to I3, right? So if I perform this row operation on I3, what I will get is I will get this matrix over here, right? Okay, so this is my original matrix, and if I multiply row 3 by 2 and I add it to this, I'm going to get a 2 showing up in this position, which is this matrix here. Right? Okay, so this is I3 and this is epsilon, right? Now, this is a row operation, and we just saw that the inverse row operation for a row operation of the form C row I plus row j, right, is minus C row I plus row j, right? So the inverse row operation of this over here is minus 2 row 3 plus row 1, right? Okay, so let's consider I have this matrix I3, right? And I apply this row operation to it, right? Okay, so what I'm going to have over here is I have I3 and I apply the row operation to it, right? And then I have I3 and I apply the inverse row operation to it, right? So this is one matrix over here. The epsilon I3 is this first matrix here. And I have I3 and I apply epsilon inverse to it, so I get this matrix over here, a second matrix, right? Now, when I multiply these matrices, right, and you can check that when you multiply these matrices, you will get the identity matrix, right? Okay, so what that is saying for you, according to this definition, is this is an elementary matrix over here, epsilon I3, right? And this is the elementary matrix where instead of using epsilon, I use the inverse row operation, right? Okay, so this is epsilon I3 over here. And this is an elementary matrix where I use the inverse row operation, right? And it turns out that this matrix here, when I multiply it by my original epsilon I3, I get the identity, right? So what that is saying is that this matrix over here is the inverse of the epsilon I3, right? So this here is the inverse of this matrix, right? That is satisfying that AB is equal to the identity, right? So this is the A over here, this is the B over here, is equal to the identity over here, right? Okay, so this matrix here is the inverse of this one, right? Okay, so this is the epsilon I3, right? Okay, and so the inverse of the epsilon I3, in other words, okay, so this is the epsilon I3, and this minus 1 means it's the inverse of the matrix, right? Okay, so the epsilon I3, so if I have this matrix epsilon I3, the inverse of it is this guy over here, right? So the inverse of epsilon I3, this is epsilon I3. The inverse of this is this one over here, right? And this one over here is I3 when you apply the inverse row operation to it, right? Okay, so the notation could be somewhat a little confusing over here, but how you want to read this is, if you forget about this over here to start off with, what I have over here is I have an elementary matrix, right? And if I want to get the inverse of it, right, in order to get the inverse of this elementary matrix, what I do is I take an identity and I apply the inverse row operation, the corresponding inverse row operation, right? And that would give me the inverse of this one, right? Okay, so one more time, right? If I want to get the inverse of this elementary matrix, so this one over here, right? This one over here is corresponding to the row operation epsilon 2 row 3 plus row 1, right? So if I want to get the inverse of this matrix, what I do is I consider the inverse row operation, apply it to this, that would give me this, right? And this over here would be the inverse. Okay, notice this is a very fast way to get an inverse, right? So in the case of elementary matrices, it's very fast. You can get inverse matrices very quickly, right? So if I have an elementary matrix over here and I want to get the inverse of it, I just need to determine what's the row operation corresponding to this elementary matrix, take the inverse of that row operation, apply the inverse to that of this row operation to the identity, and this would give me the required inverse, right? The required inverse is this over here, right? All right, so let me just clarify a little bit, right? This is I3 over here. This is this 3 by 3 identity matrix, and I have this row operation here, right? Okay, so what I can do is then I can apply this row operation to the identity matrix, right? And when I apply this row operation, which is add in 2 times row 3 to row 1, I would get this matrix over here, right? With a 2 over here, right? So this is I3 after I apply this row operation, right? And what I want to do is I want to get an inverse of this elementary matrix here, right? And to get an inverse of this elementary matrix, right, which is this notation, right? So I want to get an inverse of this matrix here, right? So it's the same elementary matrix. I want to get an inverse of it. How I do that is I get it by looking at this row operation over here, right? The epsilon, right? Taking the inverse of that row operation, which is this here, right? So the inverse of this row operation is minus, if this is 2 row 3, this would be minus 2 row 3 plus row 1. And I take this inverse row operation and I apply it to I3, right? When I apply it to I3, I will get this here, right? When I apply this inverse row operation to I3, I'd have a minus 2 showing up over here, right? Okay, and the point is that this here, this with the minus 2 over here, that is the inverse of this elementary matrix, right? So to get the inverse of this elementary matrix epsilon I3, to get the inverse of this, right, what you do is you look at the row operation corresponding to this elementary matrix, you find the inverse of that row operation, you apply the inverse of that row operation to the identity, right? And that would give me this, and this would be my required inverse here, right? So what I just did is an example of theorem 3.27, right? If I have an elementary matrix such as this one over here, epsilon I3, right? Every elementary matrix would have an inverse matrix, right? So every elementary matrix such as this one would have you'd be able to find an inverse matrix. And how you'd find the inverse matrix is you'd look at this row operation here, right? Epsilon. You find the inverse row operation, which is the epsilon inverse, right? Find the inverse row operation. Apply that inverse row operation to the identity, right? And this inverse row operation applied to the identity would be the required inverse, right? Okay, so that is this equality here, right? So this example that I just did is an example of Theorem 3.27, right? And the proof over here, it's in the notes. You could always take a look at it, right? Right, okay, and here we have this definition for n by n matrix to be singular or non-singular, right? So a square matrix is non-singular, right? So n by n matrix is non-singular if the rank of the matrix is equal to the size of the matrix, right? In other words, the number of columns or the number of rows of the matrix, right? Okay, and it's singular if the rank is less than the size, right? Okay, so what's an example of this? Here I have this matrix A over here. So A is this 3 by 3 matrix. And, well, what's the rank of this, right? In order to get the rank of it, we know how to get the rank of it. The rank is the dimension of the row space, but how you calculate the rank is you can apply Gauss-Jordan to this matrix over here. When we apply Gauss-Jordan, we would get, in this case, an identity matrix over here, right? Okay, so the number of non-zero rows, this is an RRAF, the number of non-zero rows over here is 3. So the rank of this matrix that I started off with is the number of non-zero rows. Number of non-zero rows is 3. So rank of A is equal to 3, which is the size of the matrix. So that satisfies this condition, right? I have a 3 by 3 matrix, right? With rank of it being 3. So this is an example of something that is non-singular, right? To see an example of something that is singular, right? Consider this matrix over here. Here I have two zero rows on top and a non-zero row on the bottom, right? If I apply Gauss-Jordan to this, right? What I would get is I would get one non-zero row and 2 0 rows, right? what would happen is if I apply Gauss Jordan to this non-zero row would go on top, and the two zero rows will show up on the bottom, and I would in fact get 1 0 1 third 0 0 0 0 0 0, right? Okay, so that matrix would have one non-zero row, so the rank of this matrix here is 1, right? And the rank of the matrix is 1, which is strictly less than the size of the matrix, which is 3, right? So this is an example of something that is singular, right? So this is a singular matrix, okay? Okay, so you want to recall that a matrix A is invertible, right? If I can find some matrix B that satisfies A times B is equal to the identity, right? Okay, so a square matrix A is invertible if I can find a matrix B such that A times B is the identity of A, right? Okay, and over here what I have is a matrix is non-singular, right? A square matrix is non-singular if the rank of A is equal to the size of the matrix, right? Okay, so you probably know from or you heard from 1180 that if a matrix is invertible, right? Well, if it's non-singular, it's going to have an inverse, right? But that actually requires a certain amount of proof, right? Because here the singularity or the non-singularity depends on the rank, which is the dimension of the row space. And here the invertibility depends on the existence of an inverse, right? Okay, and well, I guess a third condition is looking at determinant, but we'll get to that eventually, right? Okay, so invertibility here is existence of the inverse, right? So if I have an A over here, can I find a B such that A times B is the identity? And non-singular means that the rank of A is equal to the size of the matrix, right? Okay, and it turns out that those conditions are equivalent, right? So that is what theorem 3.29 is saying, is that if I have an n by n matrix, then the n by n matrix is invertible if and only if it is non-singular, right? So it's invertible if and only if the rank of A is equal to the size of the matrix, right? Okay, the proof of this theorem is in the notes, right? But what's nice about this proof is one direction. So, okay, so if I need to prove this, right? This is if and only if means that if it is invertible, then it is non-singular. So that's one thing that you'd need to show. And then the next direction is you need to show that if the matrix is non-singular, then it is invertible, right? So you need to show two implications, right? So that is what these arrows mean, right? This first arrow is saying that, well, okay, you're going to assume that it's invertible. And now what you want to do is you want to show that it is non-singular, right? Okay, and then the second direction is if it is non-singular, right? You assume it's non-singular, and then you want to show it's invertible, right? Okay. Now, given if it is non-singular, right, to show it's invertible, this proof is well, this is the only direction that I will look at, right? If you're interested, you could look at this direction, but let's look at this direction here, right? If A is non-singular, then it is invertible, right? And this direction is nice because it in fact gives you an idea how to actually determine an inverse, right? By using row operations, right? Okay, so I won't go through the details over here of this direction, right? But I'll show you an example of how it works, right? Okay, so we're using this example over here for matrix A, right? All right, and it's and let's work with this matrix A over here. We apply Gauss-Jordan to it, right? And when we apply Gauss-Jordan to it, we get this RRAF with 3 non-zero rows in it, right? Okay, so the rank of this matrix is 3, right? Which is equal to the size of the matrix. So by definition, it satisfies this condition that the rank of the 3 by 3 matrix is equal to 3. So your matrix here is non-singular, right? So we know that it's non-singular, right? Okay, so now that we know it's non-singular, right? Right, and we actually show that it was non-singular by using Gauss-Jordan, right? If it is non-singular, if I have a non-singular matrix and I apply Gauss-Jordan to it, what I will always get is I would always get an identity matrix in the end, right? So if I have a square matrix over here and a non-singular square matrix and I apply Gauss-Jordan to it, I will always get an identity matrix over here, right? If you didn't get the identity matrix, right, that would mean that you would actually end up with a 0, right? Which is not possible because you're not supposed to get any zeros because it's non-singular, right? Okay. So if it's non-singular, you would always get an identity matrix over here, right? Okay, so what that means is that given my original matrix A over here, right, I apply row operations to it, and in this case I apply two row operations, and I would end up with an identity matrix, right? Okay, so I have my matrix A over here, and when I apply these two row operations, epsilon 1 and epsilon 2, I get the identity matrix, right? So A, apply first row operation, which is epsilon 1, then apply second row operation, which is epsilon 2, would give me the identity matrix, right? Okay, so, well, remember we saw this, right? If I have, and this is, right, this is Lemma 3.24, right? Part 2, right? If I have a sequence of row operations applied to a matrix A, right, I can achieve those row operations by multiplying by elementary matrices, right? So I can achieve the row operations epsilon 1 and epsilon 2, right, on A by multiplying by suitable elementary matrices, right? And the elementary matrices that I'm going to multiply by, first one would be epsilon 1 applied to I3, and the second would be epsilon 2 applied to I3, right? Okay, so what is this saying for me, right? Well, I have A over here, and when I multiply by these two matrices here, right, I get the identity, right? But that actually is good enough to tell me that from my definition of inverse, right, that if I have a matrix A and I multiply by some matrix B, then this is the inverse over here, right? So these two together, this product over here, this is going to be my required inverse, right? So notice I'm getting my required inverse via row operations, right? Okay, so I'm saying that these two epsilon 2 I3 times epsilon 1 I3, right, in this order, this is I'm gonna call that B. And that B is the inverse of the matrix A because your B times A is the identity matrix, right? Okay, and I write that out over here, right? If I have B, which is epsilon 2 I3 times epsilon 1 I3, right? Then the fact that B times A gives me the identity means that B is equal to A inverse, right? So A inverse is equal to B. B is the product of these two elementary matrices, right? And I can always work out what these elementary matrices are, right? This, all I need to do is take the 3 by 3 identity and apply epsilon 1 to it, right? Okay, so if I take this, this is epsilon 1, right? And if I apply epsilon 1 to 3 by 3 identity, I'm going to get a minus 2 over here, right? And if I have identity and I apply epsilon 2, I'm going to get a minus 3 over here, right? Because what you're doing is you add in minus 3 row 3 to row 2, so I get a minus 3 over here, right? Okay, so this first one here with the minus 3 is epsilon 2 I3, and this one, second matrix over here with the minus 2 is epsilon 1 I3, right? And notice that these two are elementary matrices, right? And the product of these two matrices would be a next matrix, right? And the product of these two matrices, right, which is this next matrix, this in fact is your inverse, right? Right, so notice we in fact got the inverse of A over here, the matrix A over here, by in fact using these row operations over here, right? This matrix A, we keep track of the row operations, epsilon 1, epsilon 2. Using these row operations, we form corresponding elementary matrices, right? Okay, and when we take the product of those corresponding elementary matrices, we in fact got the inverse, right? And that is what is we saying over here in this direction of the proof, right? I have a matrix A that is non-singular, right? And what I'm going to do is I'm going to apply Gauss-Jordan to it until I get identity matrix over here, right? So the Gauss-Jordan algorithm would transform in the case when A is non-singular, right? The Gauss-Jordan algorithm, right, such as Gauss-Jordan algorithm applied to A, would result in an identity matrix, right? Okay, and then what you want to do is you want to keep track of those row operations that take you from A to the identity matrix. In this case, it's just two of them, epsilon 1 and epsilon 2. Epsilon 1 and epsilon 2. It could be more in general, so that is the more general case here. It could be small p, right? Row operations, epsilon 1, epsilon 2, and epsilon p, that would take you from A to the identity matrix, right? And the required inverse, right, following an argument similar to this, right? The required inverse for A would just be a product of elementary matrices, right? So for each row operation over here, you form your corresponding elementary matrix, right? And then the product of those elementary matrices would be a required inverse. Alright, so let's look at an algorithm for getting the inverse of a matrix by using row operations. Right, so that's just theorem 3.30, right? Okay, and the method hinges on the example is illustrated by the example that I just did, right? So what you have is you have a matrix A. When you apply row operations to it, right? If you get an RREF, or if you get a identity over here, if your Gauss-Jordan terminates an identity, right? Then what you do is you keep track of those row operations, right? And when you, for each of those row operations, you form corresponding elementary matrices, and the product of those elementary matrices would be a required inverse, right? Okay, so that is how this algorithm is going to work, right? What it's going to do is you're going to have your matrix A that you're going to start off with, right? All right, you're going to apply Gauss-Jordan to it, right? Somehow you're going to keep track of these row operations, right? And you're going to keep track of the row operations and the corresponding product of elementary matrices, right? And when the algorithm terminates, right, this would be the answer that you would get, right? So the answer that you would get would be a product of elementary matrices, right? So this algorithm, it works using this theory over here, right? That's illustrated in this example, but you wouldn't really see it if you just work with the algorithm, right? All of this stuff is hidden inside the algorithm, right? So let's take a look at an example of how the algorithm works, right? Okay, well, how you actually calculate with the algorithm, right? Okay, so I have a matrix A and I want to get the inverse of this matrix A, right? And the matrix, of course, is a square matrix here, right? Because we're only going to be taking inverses of square matrices, right? First thing that you're going to do is you're going to form an augmented matrix. So what you have is the matrix A that you want to get the inverse of, which is this one over here, the 1, 0, 2, 0, 1, 3, 0, 0, 1, right? So you're going to have an augmented matrix, and the original matrix A is going to be on the left hand side of your separator here. And then what you're going to have is you're going to have an identity matrix on the right hand side, right? Okay, so notice that this augmented matrix is going to be basically, it's twice the size of your original matrix, right? Because this is a 3 by 3 matrix, and this augmented matrix is 3 by 3 and a 3 by 3 here. So this overall is a 3 by 6 matrix, right? Anyway, so with this original matrix, you form an augmented A together with the identity matrix over here, and you have your separator in between, right? And now what you do is, so this is A identity matrix, and that is what this is over here. I call it F, but it's not really important, right? The main thing is that this is A an identity matrix, right? So you form that first, right? Okay, and now what you do is you apply Gauss-Jordan to this over here, right? So you apply Gauss-Jordan to the entire matrix, right? So what you're going to be doing is you're going to start on your apply Gauss-Jordan in a normal way. You start with your left-hand column over here, and then you keep you apply a Gauss-Jordan, right? Okay, so for these examples, when you apply in your Gauss-Jordan, right, the ideal case is when you apply a Gauss-Jordan and you get an identity matrix on your left-hand side over here, right, which is what happens in this case, right? In some cases, you will not get an identity matrix on this left-hand side. What you would get is you'd get non-zeros, and then you would get potentially a zero row on the bottom, right? Or several zero rows in the bottom, right? Okay, so if when you doing this sort of problem, right, and you apply in your Gauss-Jordan, right, you apply in your row reduction method to the entire matrix, right, and you end up with a row of zeros just on this left-hand side, right, then you can stop, right? And you can stop, and then what you'd be is you'd be in this case 1 over here, right, where your matrix is not invertible, right? Okay, so when you're doing this problem and you end up with a row of zeros on your just on the left hand side, and you're gonna stop, and that says that the matrix is not invertible, right? Okay, I'll do an example of that, right? But what this is over here, this is a case of this is an example of case 2 over here where it actually is invertible, right? Okay, so I start off with my matrix A here, right? And then I'm gonna apply Gauss-Jordan to the entire matrix, right? Okay, so applying the Gauss-Jordan to the entire matrix, this particular matrix is already in a good form, right? So you'd start over here with 1, right? And notice there's nothing to do, right? Because, well, this is already, you have a pivot in your first, in your left hand, your top left hand over here, right? And with that pivot, what you'd want to do is you want to make everything else in the column 0, right? But it already is 0, right? So there's nothing to do. So what you do is you go to your next column, right? So you go to the next column, but in one row underneath, right? And then what you do is you want to make that 1, but it's already 1, right? And you want to make sure that everything else in the column is 0, which it already is, right? So there's nothing to do in this column. So we keep going again, right? So you drop to the row underneath, right? And now you look in this entry, right? You see it's already 1, right? And then you look in this column, right? And you notice in this column, well, not everything is 0, right? So you do have some work to do over here, right? Okay, so you're gonna be using your Gauss-Jordan algorithm here to make this 0 and make this 0, right? So first thing we could do is we could multiply row 3 by -2 and add it to row 1, right? And that would give me the 0 over here, right? But the key thing that you want to note in when you're doing this is when you multiply in row 3 by -2, right? What you're going to do is you're going to multiply throughout, right? Okay, so you're multiplying throughout over here, which means that you're going to have a -2 over here and you're going to have a -2 over here, right? When you add this -2 over here and this -2 over here to your row 1, right? What you'd get is you get a 0 over here, but you're going to get a -2 over here from this -2, right? So that's where that -2 comes from, right? So the point is when you're doing the row operations, you're doing it for the entire row, right? Not just for the row on this side, the left-hand side of the separator. You need to do it for the entire row on both sides of the separator, right? Okay, so I have this now, right? And again, what I'm doing is I'm focusing on this third column over here, right? Okay, so when in this third column, you notice you have a 3 over here, and what you'd want to do is you want to make this 3 0, right? So I multiply this third row by -3, and you add it row 2, right? So that's what this says over here. Now when I multiply this third row over here by -3 and add it to row 2, right? What I would get is 0 here, and I get a -3 over here, right? So notice what I said, you're going to be using the entire rows, right? Okay, so I have a 0 over here and I have a -3 over here, right? And now what I have is I have 1 1 over, so I have the identity over here, right? Once I have the identity over here, this is where you stop, right? Once you get the identity over here, you stop, right? And this here, this is your required inverse, right? Okay, and to use the notation in the theorem, right? What you do is you start off with A together with the identity, right? And then with that, what you do is you apply Gauss-Jordan until you get a matrix B, and with you get this augmented matrix where B is on the left hand side and C is on the right hand side, right? Okay, and if B, so now once you, so this is your original matrix, and this is when you apply a Gauss-Jordan, right? If this matrix B over here is non-singular, right? So if the rank of B is equal to n, right? Then what that would have meant is you would have the identity over here, right? Okay, so one more time, right? So this is my original matrix, the A with the um, identity matrix. You apply Gauss-Jordan until you get something over here, right? If what you have over here is the identity matrix, right? Then the inverse, your required inverse, is what's on the right hand side over here, right? This is right. So the this C over here, which is the C over here, which is the right hand side, that is your required inverse, right? So the inverse is on the right hand side, and that would be this matrix over here, right? So your required inverse of A, right? So this is A. Your required inverse of A is what's on this right hand side over here, provided this left hand side is the identity, right? So it's what's on this right hand side. So this is your inverse, and that's what this is saying over here, right? The A inverse is this right hand side. Okay, so let's use this theorem 3.30, right? So our algorithm to determine an inverse, and let's consider the case when your matrix A is not invertible, right? Okay, but to start off with, we don't know whether it's invertible or not, right? So we just have your matrix and we're gonna use your algorithm basically to investigate, right? Okay, so what you do is your matrix A over here, you form your augmented matrix, right? So A identity, right, as specified over here. You form A with your identity matrix over here. And now what you're going to do is you're going to apply Gauss-Jordan to this 3 by 6 matrix here, right? Okay, so you're applying your Gauss-Jordan in a normal way. You'd start with your pivot over here, which is 1, and you'd make you do row operations. So you're gonna get a 0 over here in this column, and you're gonna get a 0 over here in your first column, right? Okay, and when you do that, notice the row operations are going to affect the entire matrix, right? So for example, over here, this 1 over here, okay, so we use this 1 to get rid of this 2, right? And in order to do that, we had minus 2 row 1 plus row 2, right? So that gave me a 0 over here, right? But then that minus 2 times row 1 was minus 2 times 1, which is minus 2 added to this 1, gave me this minus 2, right? So what I'm saying here is that when you're doing your row operations, you're doing it for the entire row, right? Okay, so we do the row operations, and I get a 0 here, and I get a 0 here, right? And I keep going with my Gauss-Jordan, which means I need to go to the next column and look at this minus 8 here, right? And I notice over here I have a minus 8 here, and I have an 8 over here, right? So what I could do is I can add row 2 to row 3, right? And when I add row 2 to row 3, I'll get a 0 here, I'll get a 0 here, right? Notice I get a minus 2 plus 1, which will give me this minus 1. I get 1 plus the 0 over here, which gives me 1, and then the 0 plus the 1 gives me the 1, right? So you see, when I'm adding the row 2 to row 3, I'm doing it straight across, right, for the entire row, right? Okay, so over here, what I have is I end up on this left-hand side with a row of zeros, right? And once I end up with a row of zeros on this left-hand side, right, that in fact tells me that the rank of this matrix over here, A, is less than the size of the matrix, right? So the rank of this matrix A here is equal to 2, which is less than 3, right? So this matrix A, by definition, is singular, right? Okay, so A is a singular matrix, right? And because it's a singular matrix, it's not going to be invertible, right? So that's one way to see that your matrix A is not invertible, right? Or a next way to see this is that if when you do your row operations and you end up with a row of zeros, well, just on this left hand side, right? So remember, you're not to consider this row as zeros, we're not looking at the right hand side over here, we're just looking at the left hand side. If you end up with a row of zeros on this left hand side, then what that means is that the matrix A that you started off with was not invertible, right? So one more time, if I have this A over here, form the augmented matrix A with the identity, apply Gauss-Jordan, and if I end up with a row of zeros here, right, on the left hand side, then the original matrix is not invertible, right? Okay, and that in fact is case 1 over here, right? The rank of and the B over here is referring to this left hand side over here of this last 3 by 6 matrix, right? So if the rank of B is less than the 3, right, which is the size of the matrix, then the original matrix is not invertible, right? But as I said, right, if when you do it and you just get a row of zeros, then this original matrix is not invertible, right? You want to compare it. Okay, so that's it for this question, right? This matrix A is not invertible, right? But you want to compare it to the example that we just did, right? Here, when I form my A with the identity matrix and I applied the Gauss-Jordan, notice I didn't get any row of zeros here, right? On this side, I didn't get a row of zeros. In this case, what I got was the identity, right? And when I get the identity on this side, this over here on the when I get the identity on this side, right, then my original matrix A is invertible, and the inverse is what's showing up on this right hand side over here, right? So in this case, the inverse is this matrix on the right hand side.